we are going to solve these exponential equations. They're exponential because the x is the exponent. Okay, so before we get to the notes, just use some common sense here. What does x have to be equal to? X has to be equal to 5, because if the 2's are equal, then the x has to be equal to 5. If it's going to be equal, that's just common sense, right? Doesn't take a genius to figure that one out. What does x have to be equal to in this one? X has to be equal to 8. Okay. Can we figure that one out? If the 5's are equal, then the 2x has to equal to the 8. Of course, that would mean that x has to be equal to 4. The bases are equal. This is pretty easy to figure out. If the bases are equal, then the exponents have to be equal. But what if the bases are not equal? But do we know that 9 is equal to 3 squared? Isn't that equal to the 9? That can take the place of the 9. It still has the x power. So can we figure that one out? Now the bases are equal. A little bit harder. 5 equals 2x. So x would be equal to 5 over 2. A lot of these will have fraction answers. Okay, so I believe we're ready for your notes now. Okay, we are going to solve exponential equations. Let me just point out that this is in all your notes. I added this in. That has an exponent, but this is not exponential. This is actually quadratic, if you remember. This has an exponent. Why is this an exponential and that one's not an exponential? To be exponential, the variable has to have the x. That's the kind of equation we're solving, and we solve it by making the bases the same. And if they're not the same, we have to make them the same. So on example number 1, we know that 4 is equal to 2 squared. And then we still have this x right here. Now, this requires us to remember some of our exponent rules. Exponent rule says a power raised to a power, you multiply the power raised to another power. We made the bases be equal by changing the 4 to a 2 squared. And so then the bases were equal. So if the bases are equal, then the exponents also have to be equal. The bases are already equal, the exponents have to be equal. Subtract x from both sides, and x is equal to negative 3. Now, sometimes we don't remember our math facts very well, and so we may need some help on example number 2, figuring out what the bases need to be, because on example number 2, are the bases the same? No. I made this multiplication chart to help us. Now, this is not your normal multiplication chart. A normal multiplication chart, we would say 3 times 4 is 12, but that's not what it says. This is a power chart. And so what that means is this is 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power. This is 3 to the first power, 3 to the second power, 3 to the fourth, third, fourth. And so that's how it's set up. These are not These are powers. This is the base number, first power, second power, third power. Okay, so I need 9 and 27 in the same column. You see that 9 and 27 are in the same column? That means I'm going to change them both to base 3. So 9 is 3 to the second power, because it's first power, second power. That's how the chart, but you probably already knew that. 9 is 3 squared. 27 is 3 to the 1, 2, 3 power. 27 is 3 to the third power. And so then we still have the x minus 2, and we still have the 2x. And our exponent rules say that we raise a power to a power by multiplication. So I multiply a power times a power, so this is 3 to the 4x power, 3 to the parentheses x minus 2 power. The bases are the same. If the bases are the same, then I need to make the exponents the same. And I need to continue solving. Well, to continue solving, I'm going to need to distribute that 3, and so that's going to be 3x minus 6. To solve that, I need to combine like terms. I need to get my x's together, so I subtract 3x from both sides. Example number 3 has a fraction in it. Do I have any fractions in my chart here? No. And so I have to remember this exponent rule that we learned earlier in the year. If I want a fraction is the same as a negative exponent. That was a exponent rule that we learned back about January. So I'm going to have to use this rule when I have fractions. So I'm looking in my chart for an 8 and a 2. So that's going to be this column right here. So 8, 1, 2, 3, 8 is 2 to the third power. That's just the 8 part. Now, that's just a 2. That's 2 to the first power. But to make it into a reciprocal, to make it into a fraction, you put a negative in front of the power. To make it into a fraction, you put a negative in front of the power. And then we still have the x. That's the 1/2, and we have the x plus 4. The 1/2 is 2 to the negative 1 power. That's equal to 1/2. So then we use our power to a power rule. Once the bases are the same, then the exponents have to be equal. The 3x has to equal negative 1x plus 4. And then you have to distribute and solve. Negative x minus 4. Then I have to combine like terms. I'm going to add x to both sides to cancel that x out so that I can get the x's together. If you have a fraction, the only fractions we're going to look at are reciprocals. If you have a fraction, You have to use that negative exponent rule to get the correct exponent. Having a little bit of computer issues this morning. Okay, so on my chart down here, I'm looking for the 80, the 81, and the 9 in the same column. So, we have an 81 and a 9 in the same column right there. 81 is 9 squared. 9 is 9 to the first power, but since it's a fraction, it's going to be a negative 1 power. Then I'm still going to have the 3 minus x. When you raise a power to a power, the bases are equal, so you distribute and solve. Need to combine my x's. I'm going to add 5x to both sides so that when I combine it, I'm going to have a positive coefficient. What happens to my 6's though? They cancel out, and what I have left is 3x equals 0. So x equals 0.